We've now completed the proof of the extension theorem for finite premeasure spaces, following the approach in Bruce Driver's notes. I wanted to comment that a similar approach can actually be found in a somewhat obscure paper by Dorothy Maharam in 1987, and if one squints hard enough, the integration theory notes of Marshall Stone from 1948 also allude to the use of the pseudometric that we use in these notes in a construction of measure extensions. Because it's a fairly involved, if intuitive proof, I thought we'd briefly review all of the steps that we went through to achieve the final result. We started with a finite premeasure space. From that premeasure, we construct the outer measure, mu star, which is defined to be the infimum of the sums of the measures of all countable unions of sets that contain the set we're trying to take the measure of. We showed that this function is monotone and countably subadditive, which contrasts with finitely additive measures, which we showed are always countably superadditive. We then showed that if nu is a countably additive measure on a sigma field extending mu, then in fact the outer measure of mu dominates nu. So the outer measure dominates all measure extensions. On the other side, we showed that if we have a finitely additive measure, it dominates its outer measure. And the two are equal if and only if that finitely additive measure is actually a premeasure. Now, having developed the properties of the outer measure, we used it to define a pseudometric. The distance between any two subsets of omega is defined to be the outer measure of their symmetric difference. And we showed that this is indeed a pseudometric. It is a positive distance function which is symmetric and satisfies the triangle inequality. It does not, however, separate points. It is not a genuine metric, but it is a pseudometric, which is all that matters for the techniques that we need to use. We also computed that this pseudometric is well behaved with respect to countable unions, intersections, and complements, which helps to use it to establish measure-theoretic properties of the domain on which it's defined. Then we showed that the premeasure, which is a function defined on the field A that we started with, thought of as a subset of the pseudometric space equipped with this pseudometric, is actually a Lipschitz function with Lipschitz constant 1. And therefore, it automatically extends to the boundary. Lipschitz functions have unique extensions to the closure of their domain, which are also Lipschitz. That is going to be our putative measure extension, the Lipschitz extension of mu. Now, in order to get there, we established an intermediary domain between the field A and its closure, A sigma. A sigma consists of all countable unions of A. A is an algebra or field, so it's closed under finite unions, but not necessarily countable unions, so we close it up under countable union. And we went ahead to show that in the pseudometric space, this larger set A sigma has the same closure as A. And we used this to show that the identity here, that the outer measure is equal to the finitely additive measure, provided that it's actually countably additive, actually a premeasure, extends beyond just the domain A, but all the way to A sigma. The extension of the measure, via the Lipschitz function approach, is equal to the outer measure on A sigma. We also used this property, the well-definedness under unions and intersections and complements, together with this, to show that the closure is a sigma field. Pushing us almost all the way to the end, we simply want to show now that this extension actually is countably additive. To do that, we have one more intermediary step, which is interesting in its own right, describing the domain, A closure, in nice approximation terms. The closure of A consists exactly of all of those subsets that can be approximated well from the outside by sets in A sigma. That is, a set B is in a closure if and only if, for every tolerance epsilon, we can find a containing set C for B that is in A sigma with the property that the distance between B and C is less than epsilon, or alternatively, due to the containment, satisfying the property that the outer measure of C minus B is less than epsilon. And we used this approximation property, together with what we showed previously, that mu star and mu bar are equal on A sigma, to extend this identity all the way to A closure. Mu star and mu bar are equal on A closure. And we then finally used that to show that the extension mu bar is a genuine measure on this sigma field, using the fact that mu star is countably subadditive and mu bar is countably superadditive, since it is finitely additive. And that concluded the proof. Now there is one more step to the full statement of the proof, because usually we state not only that there is an extension, but that it is unique. If F is any sigma field which contains A and is contained in this closure, and nu is any measure on that sigma field which restricts to mu on the original field, then in fact that extension nu is nothing other than mu bar, restricted to F. Let's prove this. In fact, this requires the one piece on the previous slide that we haven't used yet, which is right here. The outer measure dominates all possible measure extensions. Because of that, we simply note that this putative extension, nu, is less than or equal to the outer measure of mu on the sigma field F where it is defined. Now, let A and B be any subsets of F. Then, following exactly the same outline we saw last time, drawing this nice picture relating the symmetric difference to the union and the intersection, we have that the difference between mu of B and mu of A in absolute value is bounded by nu of the symmetric difference of A and B. But that is, by what we just said, less than or equal to the outer measure of A symmetric difference B, which is the pseudometric distance between A and B. So what does that show? That shows that nu is a lip1 function of its domain. Well, Lipschitz extensions are unique, and since nu restricts to mu on the field, which is dense in A closure, and therefore in F, it follows that nu must equal the extension of mu. To be precise, if I take any subset E of F, since F is contained in the closure of A, there must exist a sequence of sets in the field A that converge in the pseudometric to E. We just saw that nu is Lipschitz continuous and therefore continuous, which means that nu of AN converges to nu of E. But nu of AN is equal to mu of AN by the assumption that nu restricted to A is the same as mu. And of course, mu of AN converges to mu bar of E. That's how mu bar is defined. Therefore, those are equal, and that concludes the proof. So we have the full measure extension theorem for finite premeasure spaces. Every finite premeasure extends uniquely to a fully fledged finite premeasure. Now, this is a course in probability, and so finite measures will do the trick most of the time for us. However, it is convenient to have some other non-finite measures, for example, the Lebesgue measure, around at times. And so we would like an extension theorem in the larger category of sigma-finite measures. It turns out that that's pretty routine to accomplish from what we've already done. Let's start instead of a finite premeasure space with a sigma-finite premeasure space. And remember that that simply means that the sample space can be decomposed into a countable union of sets, of course, in the field, each of which has finite premeasure. Now in that case, we're simply going to decompose this premeasure space as a countable disjoint union of finite premeasure spaces. We take omega 1 to be a1 in this decomposition, and omega n to be an minus 1 to produce disjoint sets. We still have omega decomposed in terms of these new sets, omega n, and in fact, it is a disjoint decomposition now. And since omega n is contained in an, the premeasure of omega n is finite. So that allows us to construct for each n a finite premeasure space. We define the premeasure mu n to be mu of the set intersected with omega n. It is routine to verify that this defines a premeasure whenever mu is a premeasure. And so we have a new premeasure space, which is finite. We can therefore follow exactly what we just finished proving and extend each of those premeasures to a fully fledged finite measure on the closure of A. Now here's the subtlety. The closure involved the pseudometric, which was defined in terms of the outer measure of the premeasure. And that means that the pseudometric implicitly depends on n. So we'll get different closures of A for different n's, which might make it seem hard to put them back together. However, we can simply restrict our attention to a common sigma field that's contained in all of them, and that is sigma of A. Because A is contained in the closure of A with respect to any pseudometric, and because that closure, as we proved, is a sigma field, the smallest sigma field generated by A is also contained in here. And so we will restrict our premeasure space to that sigma field, which is consistent as we vary n. And that allows us to define a premeasure from the original premeasure as follows. We've constructed all of these premeasures on the disjoint pieces that each have finite measure, and to get an extension of the original measure, we simply add them up. It is now easy to check that this does restrict to the original measure, owing to the disjointness of all of the pieces, and that it is a genuine countably additive measure. In general, if you add up any countable collection of measures, you get a measure. So all that's left to check now is uniqueness. Let's do that. Suppose that I have a measure nu on that sigma field, the sigma field generated by the original field A, which is an extension of the original now sigma-finite measure. We need to see that it's actually equal to the measure mu extension that we just constructed. To do that, we follow a similar kind of decomposition idea. We'll define nu n, which is going to be a measure on that same sigma field, as follows. Nu n of a set E is equal to nu of E intersected omega n, where we construct the omega n's just as we did before, a disjoint decomposition of the sigma-finite measure space into finite measure pieces. Now, for any set A in the field script A, we have that nu n of A is equal to nu of A intersect omega n. Now the omega n's were chosen to be in the field A, and therefore this intersection is in the field A. And so by our assumption, that nu restricts to the original measure mu on the field A, this is the same thing as mu of A intersect omega n, which is mu n of A. So that shows that nu n is a finite measure which extends mu n. And therefore, by the uniqueness result we just proved in the finite case, nu n must equal the restriction of the extension of mu n to the sigma field generated by A. And so all we have to do now is put those back together. For any set E in the sigma field generated by A, we can decompose E in terms of these sets omega n that decompose the space. It's the union, and in fact a disjoint union, of E intersected with omega n, and therefore the measure nu of E, since it's a genuine countably additive measure, is the sum of nu of E intersect the omega n's. That's the definition of nu n of E. But as we just saw, that's equal to the sum of mu n bar of E. And that is how we define the now we know unique extension of mu. Thus, sigma-finite premeasures always extend to sigma-finite genuine measures. Before we conclude this lecture, let's also briefly discuss some of the properties of that extension, which we saw holds in the finite case, and indeed extend fairly easily to the sigma-finite case. If we have any sigma-finite premeasure space, then in fact the unique extended measure to the sigma field generated by the field is equal to the outer measure. We also have this outer approximation property. For any set in the sigma field generated by A, and any tolerance epsilon, we can always find a containing set C, which is a countable union of elements from the algebra, and which is very close to B. That is, the extended measure of the difference, C minus B, is less than epsilon. Moreover, and this is a statement that's primarily about the finite measure case, even though we didn't explicitly state it there yet, if in a sigma-finite premeasure space we have a set B which has finite measure, then we can always, for any tolerance epsilon, find a set in the original field which is arbitrarily close to it, that is, for which the measure of the symmetric difference between A and B is smaller than epsilon. I'm not going to go through the proofs of the first two. They are by now standard epsilon over 2 to the n style extension arguments from the finite measure case to the sigma-finite measure case, and you can see the details spelled out in driver's notes. But let's go through the last property here. We want to find this approximating set A in the field to our set B in the sigma field. Well, from part 2, we know that we can find a set C that is in A sigma that contains B and whose measure of the difference between C and B is less than, let's say, epsilon over 2. Now C is in A sigma, which means that we can find a sequence AN of sets in A that increase to C. Let's take one of those ANs and look at the symmetric difference with B. The symmetric difference is defined to be AN minus B union B minus AN, and it is a disjoint union. Therefore, this is equal to the measure of AN minus B plus the measure of B minus AN. Now, AN is contained in C, so this is less than or equal to the measure of C minus B plus the measure of B minus AN. And we've arranged it so that this term here is less than epsilon over 2. As for the second term, let's note that B is contained in C, and so this is less than or equal to C minus AN. Now here's an important comment. Note that the measure of C is finite. The reason for that is that it is close to B, and B has finite measure. Indeed, C is contained in C minus B union B, and therefore the measure of C is less than or equal to the measure of C minus B plus the measure of B. We've arranged it so that the measure of C minus B is less than epsilon over 2, and the measure of B is finite. Therefore, this has finite measure. But that means we're back in the finite measure case where we already argued that this can be computed as the measure of C minus the measure, or in fact the premeasure, of AN, and that goes to 0 as n goes to infinity. Since that goes to 0, for some sufficiently large finite n, this will also be less than epsilon over 2. And we can put those two together to show that for that finite n, the measure of AN symmetric difference B is less than epsilon. Since each AN is in A, that concludes the proof. We have now fully constructed genuine sigma-finite measures as extensions of premeasures. Next, we will turn to the construction of a large class of important measures on the real line, radon measures, which include the most important example, the Lebesgue measure.